Three numbers decide whether AI scales through 2030. The first is 6 cents, the cost in dollars to train 1 billion model parameters today. The second is 2 trillion, the cumulative dollars hyperscalers will spend on AI compute through 2030. The third is 60 gigawatts, the new electrical generation capacity those hyperscalers need to bring online to run that compute. Two of those numbers sit inside the semiconductor industry. One does not. And the actual semiconductor industry view, after 8 episodes of naming the upstream winners, is that the third number, power, is the one that decides everything. This video pulls all of it together: the 8 bottlenecks, the economics, and the year the AI race is decided. To project compute through 2030, you have to model 3 curves. The first is per flop cost. Every year, the same hardware budget buys more raw computation. From 2020 to 2025, the dollars per petaflop hour fell by roughly 2 orders of magnitude. Whether that continues depends entirely on the upstream supply chain we have just spent 8 videos describing. The second curve is demand. Hyperscaler AI Capex went from $20 billion in 2020 to $400 billion in 2025, and the consensus 2030 forecast is over $1 trillion annually. The third curve is the binding constraint, what runs out first as the industry tries to spend that money. Compute scales with the slowest of the upstream layers: HBM, advanced packaging, optical capacity, power. Each layer has its own clearing time. The year a layer clears is the year the industry can spend more. The layer that takes longest to clear sets the ceiling. That layer in 2030 is not silicon, it is electricity. Start with the cost curve. Training a frontier model in 2020 cost roughly $10 million. By 2024, the same parameter count was trainable for 1 to 2 million. By 2025, the very largest models, well over 1 trillion parameters, train at 30 to 60 million per run, but per parameter the cost has continued to fall. The driver is not Moore's law. Logic density at the leading process node has slowed dramatically. The driver is everything else: better silicon utilization, mixed precision training, sparse activation, and most of all, advanced packaging and HBM bandwidth scaling. Each generation of HBM gives you 50% more bandwidth at 20% more cost. Each generation of CoWoS lets you stack more compute next to more memory. The compounding effect across these layers is what has bent the per flop cost curve down 2 orders of magnitude. The question for 2030 is whether this compounding continues. The answer is mixed. HBM4 in 2026 will continue the pattern. HBM5 in 2028 will give us another step. But beyond 2028, the physical limits of TSV stacking start to bite. Optical I/O may take over the bandwidth scaling story for the second half of the decade. The dollars per flop curve does not flatten, but the slope changes. Through 2027, expect another half order of magnitude reduction. Through 2030, the curve depends entirely on whether co-packaged optics ramps in time. If it does, the trajectory continues. If it does not, the industry hits a hard wall. Now, demand. Hyperscaler AI Capex in 2024 was around $270 billion across the top 4. Microsoft, Google, Amazon, Meta, each one spending $50 to $90 billion. That number reached $400 billion in 2025. The 2026 forecast from analyst consensus is $450 to $500 billion. The 2030 forecast is over $1 trillion per year. Where does that money go? Roughly half of it to silicon, chips, accelerators, custom ASICs, networking gear. Roughly 30% to data center construction, buildings, cooling, electrical infrastructure. 20% to the power purchase agreements, generation contracts, and the substation upgrades that let those data centers actually run. Inside the silicon spend, the biggest single line item by 2027 is HBM. The second biggest is advanced packaging. The third is optical interconnect. That is the inversion. For decades, the biggest spend in semiconductor was logic itself, the CPU, the GPU. By 2027, the biggest spend is what surrounds the logic: memory, packaging, optics. NVIDIA's revenue still grows, but the share of hyperscale dollars going to NVIDIA falls. And the critical question is whether all of this Capex actually clears. $1 trillion annual spending plan only works if the upstream supply chain can absorb it. As of 2025, every layer we have profiled, HBM, CoWoS, optical, is sold out or close to it. Capex commits cannot consume what does not exist. So the real spend will track supply, not demand. Now power. A single Hopper GPU draws 700 watts. A Blackwell draws over 1,000 watts. An Ironwood TPU draws roughly the same. A 9,000 chip pod consumes 9 to 10 megawatts of electrical power continuously. To put that in perspective, that is the consumption of a small city. By 2027, U.S. data center electricity consumption is projected to double from its 2024 level, from roughly 200 terawatt hours per year to 400. By 2030, it could exceed 800 terawatt hours, which would represent over 12% of total U.S. electricity consumption. The grid was not built for this. New generation takes years. Substation upgrades take years. Permitting takes years. This is why Microsoft signed a 20-year offtake agreement with Constellation to restart 3 Mile Island. It is why Amazon bought a 1.2 gigawatt nuclear-adjacent data center campus from Talon Energy. It is why Meta and Google are entering small modular reactor partnerships. The hyperscalers know that compute beyond a certain scale is bounded by their ability to procure power. Power becomes the binding constraint somewhere between 2027 and 2029. The companies that have already locked in baseload generation through nuclear, through hydropower, through long-term natural gas PPAs are the ones that will train the largest models. The ones that have not, will not. This is no longer a chip story. It is an energy story. And the energy supply chain is even slower to scale than the optical supply chain. Pull all 8 episodes together. ASML ships 40 to 50 high-NA EUV scanners per year. TSMC's CoWoS L capacity will reach roughly 1 million wafers per year by 2027 and is already pre-sold. The HBM trio combined will ship around 8 million units in 2027 against demand for 10 to 12. Broadcom's custom ASIC bookings now run 2 years out. Coherent's NP wafer capacity is contracted through 2028. Lumentum's MM's optical components for OCS are sold out. Power is bounded by grid construction timelines that no individual company controls. Every single layer is capacity limited. Every layer's clearing time is different. And every layer is downstream of decisions made years ago about how much to invest in capacity. The cumulative effect is that AI compute through 2030 does not scale linearly with Capex. It scales with the slowest layer, which means the industry will spend the $1 trillion per year, but the actual compute that materializes will be roughly half what the dollar suggests. The other half goes to bidding wars, capacity premium pricing, and Capex pulled forward into power infrastructure that does not deliver useful compute for years. This is a market that, by mid-decade, looks structurally different from a typical hardware cycle. Demand is uncapped. Supply is rate-limited at multiple stages. Pricing power flows entirely upstream. Margin expands at every layer that is capacity constrained. The verdict: the AI race through 2030 is decided by the layer with the longest clearing time, 3 time horizons, 3 different layers in the lead. Through 2026, the binding constraint is HBM and CoWoS, both clear by 2027 with the next generation memory and packaging buildouts. Through 2028, the binding constraint is optical capacity, NP wafers, and MEMS components. Coherent and Lumentum are racing to bring new fabs online. Whether they hit timeline is the swing factor for that period. Beyond 2028, the binding constraint is electricity. Nuclear restarts, small modular reactors, large-scale power purchase agreements. These are the projects that decide whether the $1 trillion Capex plans actually deliver compute. The companies that win the 2030 race are not the chip designers. They are the ones who control whichever layer is the bottleneck in that year. In 2026, that is the memory cartel. In 2028, that is the optical duopoly. In 2030, that is the energy infrastructure. The implications for investors and operators are stark. Pricing power is upstream. Margin compresses downstream. The model trainers, OpenAI, Anthropic, the hyperscalers themselves running their own labs, are price takers across every layer. Their valuation depends on whether they can secure capacity, not whether they have the best research. And for the chip industry, this means the most strategic decision is no longer which architecture to bet on. It is which capacity layer to position upstream of. To recap, AI compute through 2030 is bounded by capacity, not by Capex. The slowest upstream layer sets the ceiling. Through 2027, it is memory and packaging. Through 2029, it is optics. Through 2030, it is electricity. The semiconductor industry rewards the layer that gates everyone else. Exactly the pattern this series has named episode after episode. ASML, TSMC, the HBM trio, Broadcom, Coherent, Lumentum. The next utility companies that sign baseload contracts with hyperscalers will join that list. This is the 8-part synthesis. If you want the actual semiconductor industry view of the AI race, not the press release version, subscribe. The series is here. The supply chain layers are now mapped. What we will track from here on is which layer clears next. See you in the next video.